Hi, I'm Prenny. The title of my project that also relates to Jack and Tony's project was modeling the impact of small-scale surface heterogeneity on air sea fluxes. So this talk's going to be split into two parts. Part one's going to be me just providing some general background information about climate models and how processes can happen across a variety of scales that's relevant to all of our research. And then part two will be me talking about my research. Well, and then I guess part three is them talking about their research. Okay, part one, a brief introduction to climate modeling across different scales. Okay, so the Earth system has has processes that happen at a variety of different scales, and all these scales can kind of interact with each other, and these scales can be as large as like 10 to the eighth meters in space, and as small as just a couple millimeters. We want our climate models to be as representative of the Earth system as possible, but the problem is we have limited computing power. So these climate models typically end up having a maximum resolution and struggle to capture some of these really small scales. So this is actually an image of a bunch of different processes that happen often in the ocean at a variety of different spatial scales. And the ones that climate models really struggle to pick up on are typically some of these sub-mesoscale processes, the smaller ones, and molecular processes. So when we have processes that are smaller than the climate model's maximum resolution, we call those processes subgrid scale processes. So if you look at this little image of eddies here, the larger the eddy or hypothetical process, the easier it is for the climate model to actually pick up on. And then at a certain point, as the process gets smaller and smaller on spatial scale, it's harder and harder to pick up. And at a certain point, it gets so small that we call it the subgrid scale because the climate model is not going to pick it up on its own. So how do we account for these processes? There are a lot of ways we can do this, but our research group used a variety of ML-based methods to do it this summer. So what I've actually done is I'm using a neural network to kind of predict how subgrid scale processes might impact larger scale processes, whereas Tony and Jack are actually looking at a low resolution map or image that only contains these larger scale processes and figuring out where exactly on the map these subgrid scale processes might occur. So two different methods to kind of do somewhat the similar task. So I've got a couple figures up here. This is just relevant to me. I have like this little graph here where, okay, the larger eddies are what I'm going to pick up by with the climate model, which I'll get to later. And the smallest one, the subgrid scale one, that's what's picked up by the neural network or like whatever machine learning algorithm we're going to use. So same is true for Tony and Jack. This comes from the climate model, just the subgrid scale stuff comes from the machine learning that they're doing. I've also just included this picture here to kind of point out or to kind of give you a general idea of like how large of a scale is picked up by a high resolution simulation. So this is just the velocity in the meridional direction. And as you can see, like this is like thousands of kilometers in length for some of these like fronts that are being picked up, or not fronts, but like features that are being picked up. Whereas if something was like on the scale of just a couple meters or even millimeters, it would be really hard to see in this large graph here, or even maybe even on a regional map. Okay, part two, my research, modeling the impact of small scale surface heterogeneity on air sea fluxes. So I want to start by just defining the problem, which you probably have kind of figured out from the title already. The problem is that air sea fluxes occur at a variety of different scales, and they impact processes at scales both larger and smaller than them. Climate models obviously can't capture all the scales at which air sea fluxes occur at, so they don't end up capturing the subgrid scale air sea fluxes. Those subgrid scale air sea fluxes do impact larger scale boundary layer processes near the atmosphere ocean interface, which is why, in order to account for that and make our climate models more accurate, I'm developing a neural network or training one right now that is meant to find the effect of these subgrid scale air sea fluxes on larger scale processes in the boundary layer region. The idea is to eventually integrate this into a climate model. We're far from that right now. So this is just, for those who don't know, a basic definition of air sea fluxes. And air sea flux is any transfer of energy, momentum, chemical compounds across the atmosphere-ocean interface. The three types of heat fluxes I'm looking at, or sorry, air sea fluxes I'm looking at are the heat, momentum, and freshwater flux. So heat flux can kind of be thought of as a transfer of thermal energy across this interface. Momentum flux, I think a good example of that would be maybe how the wind forces currents in the ocean and vice versa. And freshwater flux mostly has to do with evaporation and precipitation of freshwater. Okay, So now these are just a couple maps of the fluxes that I've been talking about. And I've included these here just so you can kind of get an idea of what the global patterns look like with these fluxes. So for example, with the momentum flux, the areas where you'll have, I guess, the highest momentum flux are the areas where typically there is like the strongest zonal wind components. So that's like in these areas, from what I understand, I could be wrong. Then we have the heat flux over here, and the magnitude of the heat flux is much larger in lower parts of the ocean than up here in the Arctic. And then the freshwater flux, yeah, I guess like the transfer between evaporation and precipitation, that happens a lot more significantly in areas where there is not that much sea ice covering the Earth. And now to methodology. This is a wonderful graph. Thank you, Julius. So was my first step in the research I was doing. So step one was to really figure out if these subgrid scale fluxes that I wanted to like parameterize for were even computable. So step one, what I did, this is a complicated figure, so bear with me. I took some very high resolution global climate data and counted that as my ground truth. Um, on this top row, what I've done is I compute the air sea fluxes based off that high res data. And I just spatially filter to get rid of any nonlinearities. And now I have a flux that accounts for both large and small scale um, processes. And then on the bottom, I have done the same thing, but the only difference is the first step is to sort of decrease the resolution that I'm looking at. So this is my low resolution flux. So I have two fluxes, one that accounts for high and low resolution, and one that accounts for one that accounts for large and small scale processes, and one that only accounts for large scale processes. So when you take the difference, you get the subgrid scale flux, which is this Q star. So this was done for all three types of fluxes. Here's kind of what the map looks like. The only reason I've really included this is just so you can kind of see like how sharp some of the differences are between various features on these maps. Like if you remember the high resolution graphs we looked at before that captured more large scale processes, I guess if you went from one feature to another, it looked a lot more smooth than this. So it's just meant to kind of capture the variability that can occur on the subgrid scale. Okay. And then the next step I did, which is like kind of the most significant step this summer, is like extensive amount of testing to just check if the fluxes I calculated were anywhere close to the fluxes that were calculated in this very high resolution run. So this like ground truth run. It turns out that yes, for the heat flux, and momentum and freshwater flux, I'm off by just a little bit every single time. And this is actually building upon what Julius has done previously. He presented this as a poster at the NSF site visit. And so my fluxes did match Julius's here, which gave me a lot of confidence. But aside from that, there was like a lot of testing. I'm still trying to figure out why this gap is there. I'm also trying to figure out whether it's like useful to like create an ice mask, which kind of excludes the parts of the, I guess, ocean that might be covered by ice. So I don't end up, I'm only calculating air sea fluxes, not like sea ice air fluxes. And so this is just a summary of all those tests that I'm happy to go into more detail about later on if you have more questions. But yes, the sanity check was clear enough that it like cleared me to at least try the neural network training. So for the neural network training, I haven't gotten too far yet. But the way have set it up so far is I'm inputting the low resolution heat, momentum, freshwater flux, whatever I'm looking for, and then various low resolution input parameters such as the wind speed, sea surface temperature. And the idea is that I output a parameterization for each of these air sea fluxes. And so this parameterization is meant to account for how the subgrid scale air sea fluxes impact larger scale processes at the boundary layer. Okay, that's me. And now I'm going to oh wait, sorry, that's an FAQ slide. This is for Jack and Tony.
So hi, my name is Tony Manriquez. I'm an undergrad at MSU Denver studying meteorology and physics. And this summer I worked with Jack Alfondre, Yu Wang, Jingweng Liu, and our PI, Dhruv Balwalda, with our project, super resolution of sea surface height using machine learning. So as Prani mentioned in their slides, air-sea interactions are a really complicated system that involve dynamics, thermodynamics, and biogeochemistry, but it's a really useful tool to understand and build climate models. Given my background in meteorology, this project was really helpful in actually making the connection between the ocean and the atmosphere, especially as an undergraduate. We currently use satellite imagery to kind of understand what these air-sea interactions are doing. So The resolution isn't the best to actually know what's going on in really great detail. As you can see from this figure on the left is a low resolution image from a satellite compared to the one on the right. And for our project, we wanted to see if we could build a machine learning model that'll take that low resolution image and then create a high resolution image. So to start, we used a high resolution ocean model from MIT called LLC4320. What this allowed us to do is pick a specific region in the ocean and then build a high resolution image data set. We focused on sea surface height for our project. So after building the high resolution image data set, we then can filter it out to create a low resolution image data set. And from building that low resolution data set, we then are training a machine learning model that'll take that, reconstruct it, and build a high resolution image data set. So this is just kind of a big picture of what it looks like. And as you can see from the high resolution image, it's a bit more jagged, hopefully, than the smooth image from the low resolution. And to help explain how we built that data set, I'm going to pass it to Jack.
Thanks. So essentially, in order to do this, we had to start out by creating two data sets in order to train the machine learning model. So one of the data sets, the first one you can see is this one is essentially one region in the ocean that was 1280 by 1280 pixels. And in that region, there are 76 different times at which each image was recorded. So we essentially divided that 1280 by 1280 size into 100 smaller 128 by 128 images. And we compiled those into a data array, an X-array object, which had 100 different locations, each one of those locations with 76 different times, and then each of those times corresponding to a 128 by 128 pixel image. And our other data set, as you can see right here, was in the same, was basically, we took our unfiltered data set that we got directly from the high resolution image, and we used this downscaling method to essentially turn the original image into a lower resolution, more grainy image that we saw earlier in Tony's slides. And these images were each 16 by 16 pixels, but with the same amount of the same locations the same locations as our unfiltered data set. As you can see, 100 different locations, and each one with 76 different times that they were recorded at, so that each low resolution image had a corresponding high resolution image. And from there, once we had our data sets, in order to convert them to tensor objects in order to feed them to our machine learning model, we used the following code right over here, which basically took our times and the 100 different locations and multiplied them to get them together in one dimension. So that way, the shape of our tensors only had one channel, which is the second dimension, and was able to function better in the model. And then we essentially, we converted those to data arrays and then converted those to tensors, which we were ready to use in the model. So our next step was using a U-Net model, which is a type of convolutional neural network. And we designed it to take the low resolution 16 by 16 images and scale them up to high resolution 128 by 128 images. So essentially the process should look something like this. This is a 16 by 16 low resolution image scaled up, and this is its corresponding high resolution image. These are both corresponding images in our data set. So this one isn't a model generated image, but essentially we ended up using the model, and we were still working on it by the end, but this is just a little graph of the training loss and validation loss over time. As you can see, they're both pretty large, but and only only decreasing a little bit over the 25 epochs that we tested. So the model hasn't been perfected. There's still a lot of work to do with it, but the overall idea and the overall goal that we're getting at is certainly we were certainly moving towards there before, as you know, the model just needs some tweaking, and by then we will be able to have a data set of older satellite images that we could get higher resolution data from. These are our citations.
Okay. Questions?
I have a question about, can you go back to the unit slide? I'm really curious as to like, so you're portioning or you're making this a high resolution image. And I'm wondering, while model training, are you doing some kind of normalization for the image for the input images? Or are you just, keeping the raw pixel values what they are? Because my suspicion is that it could very well be that this scaling up is introducing like maybe like artifacts that your model is not able to do pick up because you're sort of smoothing out. So I was just curious if you normalize the images for it.
So you're asking, like, is there like a normalization factor before? Okay. Yeah, so well, what we were doing right now is essentially just the exact code to downscale it, I believe, just takes an average over a certain amount of pixels and just combines those into one. So like in the 16 by 16, each pixel would be an average of a group of pixels in the high resolution image. So that way it's scaling up, like it already has all the data from the high resolution images. So that way it's scaling up to, it's not really introducing any artifacts, I don't believe, that would not be accounted for. It's basically kind of just not like denoising it, but just adding more detail that the training image was created from, if that makes sense.
What are the values of each pixel on that training image? Like, are they between 0 and 1, or are they, 0 to 1,000?
Yeah, so on the little color bar, it ranges from -1.8 to -2.5, just in this example, and each of those corresponds to different sea surface heights above or below 0. So in this case, all of these different pixels would represent, like, say, if it's -1.8 meters below sea level to -2.5 meters below sea level. So this is kind of just like, a color map for the height.
And so you feed in that -1.8 to that +2.5.
Yeah.
Okay,
yeah,
got you. Thank you.
Any other questions? Yes.
It's more like a comment. So the low resolution to high resolution is from a 16 by 16 to 128 by 28. So a comment is if you scale up like a directly, maybe the performance is not that good. But the possibility is to scale from a 16 by 16 to 60 by 60 first, and then you go from 60 by 60 to 128 and by 28. It's like there's a hierarchical modeling. Maybe the performance can get better.